The goal of this video is to distinguish between two types of forces, conservative and non-conservative, and to understand how forces are related to energy. Conservative forces are forces that perform work independent of the path used. These forces do not change the energy of a system, but rather convert potential energy into mechanical kinetic energy or mechanical kinetic energy into potential energy. Most of the fundamental forces are conservative. However, the effects of non-conservative forces, such as friction and drag, are often observed. Non-conservative forces perform work that does depend on the path the object is taking. Non-conservative forces are called such because they tend to perform work that removes mechanical energy from a system, generally by converting energy into heat. As an example of a conservative force, consider the force of gravity acting on a ball. The force of gravity does work that converts potential energy into kinetic energy, but the total amount of energy the ball has remains constant. If we include a non-conservative drag force acting on the ball, some of the ball's potential energy will be converted into thermal kinetic energy as well. In the absence of non-conservative forces, the work done by gravity is equal to a negative change of potential energy and is defined as the continuous sum of the force of gravity dotted with displacement. I can drop the integral sign to define an infinitesimal change of potential energy as negative f sub g dot dx. du dx is equal to the negative force of gravity. Generalizing, any conservative force will be equal to the rate of change of an associated potential energy with respect to displacement. The negative sign is consistent with our notion that objects tend to decrease their potential energies. If potential energy changes in space, there will be a force pushing the object toward a lower potential energy. As an example, consider a sketch of a bowl. The walls of the bowl form a surface that we can plot on an axis. A marble dropped into the bowl will tend to roll back and forth along the sides of the bowl. Assuming the marble doesn't jump or bounce while it is in the bowl, it must exist somewhere on this line. Because the gravitational potential energy of the marble is directly proportional to the height of the wall of the bowl, the same sketch will apply for a function of gravitational potential energy with respect to position. When the marble is on the right side of the bowl, potential energy increases toward positive x. Therefore, the force on the ball will tend to push it in the direction of negative x. When the marble is on the left side of the bowl, potential energy increases toward negative x. So the force of gravity will tend to move the marble toward positive x. If the marble is placed at the bottom of the bowl, there is no instantaneous change of potential energy. The slope of the line is zero. Therefore, the force acting on the marble in the x direction is also zero. Consider an object that exists on a surface that carves out a different potential energy map, characterized by hills and valleys. At any point in space, the rate of change of the potential energy can be expressed as positive, negative, or zero. There must therefore be an associated conservative force acting on the object, pointing always downhill. Points at which there is no force are called equilibrium points. Notice at the top of the hills, the forces on either side of the peak will point away from that point. These points are referred to as unstable equilibria, and are akin to delicately balancing a marble on top of a basketball. It will stay there if placed just right, but any small nudge left or right will tend to make the marble fall off. At the bottom of the valleys, however, are points called stable equilibria. The forces on either side of the valley point back in. An object slightly displaced from this position will return to this position. Let's say the top of the hills lay at 100 joules of potential energy. This means that an object in this valley needs to obtain at least 100 joules to get out of this range of space. The object at the bottom of the valley has 0 joules of potential energy, but might have some kinetic energy. If the object has more than 100 joules of kinetic energy, it will be able to leave this range without any trouble. If it has exactly 100 joules of kinetic energy, it will just reach the top of the hill and then stop at the equilibrium point. And if it has anything less than 100 joules of kinetic energy, it will be unable to reach the top of the hills without extra work being performed from an external source. When the object runs out of kinetic energy, it is at a point with an instantaneous rate of change of potential energy, and so it will experience a force back into the valley. This method can be used to determine whether or not objects are able to reach points in space. Here is a block traveling at some constant velocity v0 approaching a hill of height h. We'll assume there is no friction this time. Let's choose some numbers for the mass, initial velocity, and height of the hill. Calling h 0 at the bottom of the hill, the object starts with exclusively kinetic energy equal to 25 joules. To reach the top of the hill, the block would need to obtain about 78 joules of potential energy. In the absence of any external forces, the object cannot reach the top of the hill. 25 joules of energy is only sufficient to climb about 1.3 meters, so the block would reach that point before sliding back downhill. What if we do consider friction? How will this affect the logic of our problem? While the object is sliding across a patch of ground with friction, a force of friction will act on the object. This force of friction is an external, non-conservative force that will do work on the object. Because the force of friction is always opposite to the motion of the object, friction will always tend to reduce the kinetic energy of the object. If the object slides across this entire 7-meter segment of friction, 27 joules of kinetic energy would be removed. Since the object does not have 27 joules of kinetic energy, this object will not be able to slide across the entire 7 meters. Instead, it will slide until it runs out of kinetic energy, which will be about 6.5 meters in. Then the object will stop moving, and since there is no gradient of potential energy, the object will remain at rest. An important point is that if an object is sliding across a floor, the work done by friction will be dependent on the path it takes. A longer path will result in more work being done against it, so more energy will have to be put into the object to get it to its destination. The takeaway message is that non-conservative forces, unlike conservative forces, are indeed path dependent.